And you can see it every day. There is this vector diagram I showed you originally. This splitting compression, the Pacific. There's the Australia coming into it, the ring of fire. It's all coming around, and it's exactly 180 degrees away from the Rift Valley. This is a major moment. I can now calculate the forces. You'll get a very good estimate of what's breaking it apart and not rely on some convection currents. This is, I feel, a major breakthrough. I went to no expense to just have a look at the centripetal forces. I purchased the salad bowl from Tesco for £1.30. It had a nice lip on it, so I could machine up a round board, clamp it to it, and put 4 slots in with nuts and bolts varying in weight by a ratio of 3:1. And this is my Scottese moment, because I want to see if I rotated this, would this Pangaea move north and what would happen. So there we are. They're all gone to the top. Oh, it's gone into the next picture. So this would also explain why we've got this as a possibility. It could explain the divergent margin in the bottom of the Atlantic near to South America, which is in the middle of the metal, which might explain that the Antarctica has been moved. While that was being moved north, this was being moved south to surround the South Pole and occupy a larger area. This is a discussion point, but at least it's a logical one as to why you've got this divergent margin in the middle of oceanic lithosphere. And my own moment came now when I realized that observation as a child at Miller School or Start University, I've gone from an observation to an equation. This observation of 1,000th of the undisturbed sedimentary beds has resulted in my being able to get an equation. I now understand how and calculate now the forces needed to raise the South American plate out of the Earth, sea, and go on top of the Nazca plate. Tectonics is now a calculatable, or at least estimatable. You can estimate it. This is new. It wasn't ever done by anybody else. So my little mantra, in order to understand something, you must be able to measure it. This is my Eureka moment. And in 2010 or 11 or thereabouts, I was sent these unsolicited notes from Eureka. The angular momentum and plate tectonics, an analysis of the effects of angular momentum by Steve Tita and Stefano Fenu. The time I got this lot, I could not find them anywhere. I'm still looking for these gentlemen. And this is the abstract. The Earth's center of gravity is dynamic and stochastic based on exertions of mass on the crust of a half of continental plates. This investigation considers a number of dimensions influenced by dynamic changes in rotation, angular momentum, and gravitational influence, the use of mathematical modeling of the Earth's rotation using the Euler-Liouville formula, plate reconstruction software that developed by the international team at the Earthflight Project, variation in the Earth's periodicity of acceleration, the application of the Maurer wave transform, and on the next page, the division of the Planetary Science of Caltech and the Center of Geodynamics for the Norwegian Geological Society, and a modified form of the equation for the center of mass of an obscurating sphere is used by Maurer 2001. Now they put my name there with the big boys. And they've written as well, the aggregation of plates has a significant impact on the Earth's center of mass, confirming the hypothesis that gradual changes in the Earth's rotational axis and velocity largely ignored in plate tectonics. They've had the same trouble with geologists, has a significant impact on seismic events and tectonic movements. There was one other page on this, that's unsolicited notes, and there's my formula, and this has been the Earth's center of mass, and that's on its rotational dynamics. By adopting the formula used by R. Maurer 2001 for for the angular momentum of tectonic plates, we can discern the fluctuation in eccentricity. A significant difference results from minor change in mass. So at that stage, these Thai people have come to the same, using my equation alongside their work, have come to a similar conclusion, but still having trouble getting a publication. We're now finished with this part of the lecture, and we've gone on for a while. We're now going to introduce the concept of momentum is now going to be introduced in tectonic moments, because we've now separated the forces that break the supercontinents apart. But let's see what happens when the supercontinents are on the move. This is quite exciting stuff too, to me anyway. Here is the start of, there is the supercontinent. It's called Pangaea, because I didn't have enough room to write supercontinent. There, the continent has gone from 0 velocity to velocity of 15 millimeters a year, which is not exactly any significance about the length of time it takes your fingernails to grow. But the mass is enormous. No different, in fact, to Lewis Hamilton or Max Verstappen starting the grid at the red light. By the time the first chicane comes, his car has got momentum. He's got his foot on the accelerator, and if he smacks in anything, it's an almighty accident. And at that stage, we've now got the mass is now moved from 0 velocity to the velocity that's presently moving at, and we now say it's got momentum. It's on the move, and momentum is mass times acceleration. Acceleration is the present velocity minus the initial, which was 0. So I can show momentum as mass times velocity. So momentum is not mentioned as a force in the literature survey. It could be a possible new introduction to plate tectonics. I believe it is. And we'll now come on to the second stage of seafloor spreading. This is your seafloor stretching we discussed earlier. At the MR, I said had a 0 force, and we're going to change its name in a minute. Professor Shiga, we discussed this, despite the fact the internet, him in Japan, me in the UK. And there's Pangaea, there is the continent moving away. As it moves away, it splits the mantle, and it actually is now seafloor stretching, not seafloor spreading anymore, because the minute you've busted it apart, all your transform faults have stopped. So we've stretched the sea. And all the black and red lines are showing on this particular cartoon I've made up is basically the polarity changes due to the polar changes in the sun. So seafloor stretching on the first part of tectonic motion is basically now seafloor spreading. I'll put this into the vocabulary. And now we got said, as soon as this continent moves, it will move over the lithosphere on the other side. Now, there's the force due to the weight. There's the force due to the circumferential surface forces. There's your magma extrusion on your seabed at the mid-ocean ridge. And circumferential breakup causes rifting to occur. And this will initiate subduction. So this is the start of your subduction cycle. It's simply a case, this heavy weight is moving over the lithosphere and it's pushing it down. And there's no difference in form to my hero, Fred Dibner, with his lovely steamroller pushing asphalt into the road. This heavy weight is now the start of subduction. Nothing to do with convection currents. This is weight has got to overcome the bending stress of the lithosphere. It's no different to if you need to bend the pipe, you've got to know its strength to bend the pipe or flat plate, and the buoyancy, because this density is now higher than that of the lithosphere. So you've got to push this. If this was a tennis ball, you'd have to push it very hard to keep it underwater, but it's that weight that does it. So subduction, in my opinion, starts at this point. We now start subduction. This has a number of ramifications. As it goes further, this lithosphere goes deeper and deeper, and you get what we call slab-pull. Slab-pull is credited with being the major force causing tectonic movements. Let's have a look at this realistically. How the slab pull, as I said earlier at the beginning, this going down, pull this across it. It's no different to you lying in a lovely soft mattress, and as you sink into the mattress, the quilt comes over you with no trouble at all. Doesn't really happen that way. So what's happening is this is moving over, and this is going in, finally into the mantle, past the asthenosphere. The sea spreading is zero, or stretching zero, and the forces overcome for subduction to occur, that this weight must push this down and keep it down. So we're reliant on the strength of the oceanic lithosphere and the crust on top of it. But bingo, what happens when that breaks away, which it does, but the continental mass still moves. It hasn't stopped. This is another Eureka moment. The loss of the slab and the so-called pull of this continent is gone, but it's still continuing to move, and it's still compressing and pushing up all the wedging in front of it, the accretionary wedge, to give us our lovely topography when it's taken above the surface, the lovely hills and downs we walk on. But it's lost its force. Tectonic plate movements are now independent of subduction. Slab pull force is zero. This is a major moment, in my opinion. We've now separated tectonic forces which break up the supercontinent from the subduction, which is now a consequence of this heavy weight moving over the lithosphere. Convection currents have a passive rather than a role in tectonics. Mr. Hess, we've got a competitor. Quite a vicious little bugger. And there it is, after slab break-off, the loss of slab pull, the continental plate continues to move on its own momentum. The only thing that will stop that is if it hits another convergent margin. That's the only time that it will be stopped. But once that's broken away, the recycle starts, and then you get some more accretionary wedge, and so you build up your continental topography. And this is the cycle which I now ascribe to the subduction cycle. This in no way interferes with the work done by eminent geologists over the last 70 years. All I've done is I've changed direction. Instead of saying I'll pull this down to pull this along, I'm now pushing it. The work they've actually done on the lithograph, on the lithosphere, is very, very valid, and I'm not challenging that. There's the downward weight there, calculatable. It's now calculatable, the downward weight. We know the weight, we know the distances traveled, we know this depth. We can now calculate what is the strength of the oceanic lithosphere. You can put all the bending stress of the OL can now be estimated by considering this as a supported cantilever. There's all my forces. Continuous movement of the continental plate is due to the gain momentum independent of slab pull. Subduction is initiated by the downward force of the overriding continental plate. Movement of CP is unaffected by breakoff. The downward force overcomes the buoyancy force this way and overcomes the strength of the lithosphere. And in fact, we can now draw a vector diagram, which is in every textbook in applied mechanics. This is a cantilever with a distributed load on it, and it's supported underneath. We can now calculate the strength, the bending stress of the lithosphere. Professor Gaynor at Oxford University, I'll be looking to see, hopefully together with Professor Shiga, Alan Wheeler, Professor Bezard has said he wants to, like to embrace him. I've seen his paper. He's a superb mathematician to work out, to see if it's possible to work out a general formula for determining the strength of the lithosphere. And there, if the case of the Andes, there's the Nazca plate, there is the South American plate. I've shown it small, I've run out of space. As it goes over, it distorts the asthenosphere, and as it wears away from the top, you expose the oceanic lithosphere and these beautiful stromatolites up at the top of the Andes.